Hello, my name is Jared Signor, and I will be presenting my research on the simulation of chemical compound formations around star-forming regions. Throughout my research, I was assisted greatly by Dr. George Hassel. This project incorporates data from observations taken by the Atacama Large Millimeter Array, or ALMA, in an unbiased protostellar interferometric line survey of the system IRAS 16293-2422b. This project also utilizes data obtained by the spacecraft Rosetta on the comet 67P Churyumov-Gerasimenko. This data was analyzed by Maria N. Drozdovskaya, among others, in a research paper that I have cited at the end of this presentation. IRAS 16293-2422 is a binary system and one of the closest solar-like systems to ours. It is still in its infant phase of progression, and many believe it has the building blocks to produce life. IRAS is a common system to research due to it having such high potential for life. Recently, a simple sugar has been found in this region, which is groundbreaking for the life-bearing qualities this section of space contains. The Atacama Large Millimeter Array is an array of 66 radio telescopes located in the Atacama Desert in Chile. These radio telescopes observe electromagnetic radiation at millimeter and submillimeter wavelengths, which is used in the examination of molecular clouds and cloud cores, of which form the basis of a protostar. These radio telescopes can observe chemical abundances in these molecular clouds in order to better understand the processes of star formation. Comet 67P is a Jupiter family comet and has been closely monitored by an interplanetary spacecraft called Rosetta for over 2 years. Rosetta houses several tools that can be used to study this comet and was able to identify molecules stemming from the comet and the abundances of them over this 2-year period. Rosetta ended its monumental study of Comet 67P with a crash landing onto the comet itself. Maria N. Drozdovskaya has since analyzed the data obtained by Rosetta, and that, along with the data from ALMA, is what we have used to compare our simulated data. The code used to simulate these chemical processes takes in a given set of parameters, and using these parameters generates data on what chemicals are forming and the abundance of these chemicals in a protostellar gaseous cloud over millions of years. By changing these parameters, we can gain a better understanding of how to simulate realistic molecular formation and evolution. The main two parameters we will be varying are the temperature of the simulated gas clouds and whether or not the model simulates gas-grain reactions. Gas-grain reactions are chemical processes such as molecular formation involving solid dust grains embedded in these gas clouds. The code we use generates data for hundreds of molecules. However, for this presentation, we will focus on 3 main compounds, beginning with methanol. The plot on the left shows a simulated chemical abundance progression of methanol over millions of years. There are 5 main curves being plotted here, as well as 2 lines. The dotted line is the observed data from the protostar in IRAS 16293-2422, and the dashed line is observations from Comet 67P. The main factor that differentiates the 5 curves is whether they incorporate warm-up and to what temperature, as well as whether they incorporate gas-grain reactions. For these plots, the blue curve has no warm-up and no gas-grain reactions. The green has gas-grain reactions but no warm-up, and the rest have both gas-grain reactions and warm-up, but to different maximum temperatures. For a more digestible view, you can see the curves here plotted in a tile formation. The abundances are taken relative to water in all datasets here. This is done to make it more clear when comparing species of molecules and to keep all data consistent. The time period we are most interested in is between 10 to the 5th and 10 to the 6th years. The warm-up for these models begins around 10 to the 5th years as well, and takes about 200 to 300,000 years to reach max temperature. In these plots, you can see that the simulated values for the abundance of methanol are similar to the observed abundances around 100,000 years. The most similar seems to be the green curve, being a constant temperature of 10 Kelvin with gas-grain reactions included. However, almost all of the curves are fairly accurate around the important time period. This plot shows the confidence level for methanol at each set of parameters. The method of calculating the confidence level is a statistical function that calculates the quality of the fit of the curves compared to the observed data. The function compares the log of the observed values with the log of the simulated values to obtain a value between 0 and 1 that determines the quality of the fit, with 1 being a perfect fit, and as the fit decreases in similarity, the value approaches 0. The dotted line is an acceptable fit, so anything above that is a relatively similar fit. On the left, you can see the confidence level with the data from the protostar, and on the right is with the comet. We can see that all of the models spike right around the 10 to the 5th or 100,000 year mark, which is what we want. We would say that this data is fairly accurate all around, but the best fit appears to be the 10K curve. NH2CHO, or formamide, is the next complex compound we'll look at. On the left, you can see a plot of the simulated abundances of formamide compared to that of the comet and the protostar, being the dashed line and the dotted line respectively. Here you can see that there seems to be a large abundance of formamide compared to the comet and the protostar. However, barring the blue curve, of which excludes gas grain reactions and warm-up, from 10 to the 5th to 10 to the 6th years, the curves seem to be fairly similar to that of the observed values. Here we can see the plot separated into tiles once again. We can see that the abundance of formamide is large early on, and once the warm-up begins, for the latter two models, there seems to be a spike in abundance followed by a sharp decrease. The 30K model appears to be the most consistent over time in its abundance, while the green 10K model, of which incorporates gas grain reactions, seems to be the best fitting curve overall. However, it is slightly high in abundance over the 100,000 to 1 million year range. Here we can see that the 10K model appears to be the best fit for the protostar data, although it drops off for the early portion of the time range we want. While the 100K and 200K models seem to be consistent with each other, spiking at around the 100,000 year mark, then dropping in confidence after that, which is not bad. The closest fit to the comet appears to be the 30K model, of which has a strong confidence throughout most of the time range we want. Ammonia is a more simple molecule than the previous ones. Here we can see some of the plots to be relatively similar to the observed data, however they are sort of all over the place, making it difficult to see where each curve is at a given time. So we'll look at a tile formation to get a better idea of how the curves line up. Now we can get a much more clear view at each curve. It appears as though the 10K model with no gas grain reactions seem to have the most consistent curve overall. The 30K curve appears to miss the mark just before the time period we want, and the 100 and 200K models seem fairly similar, both hovering around the observed data at the time slot. However, the 200K model drops off in abundance much more drastically in its dip. Overall, the plots are seemingly very similar, but most of the differences occur right at the time slot we're looking for. Here we can see that the confidence level for ammonia fluctuates much more rapidly than the previous plots. It also appears that, as expected, the blue 10K no gas grain model has the closest fit with the protostar data. The 100 and 200K models are fairly accurate in the time range we wanted for both the protostar and the comet. However, the 30K model has easily the worst fit we've seen so far, in the 10 to the 5th to 10 to the 6th time range. This plot takes into account the confidence level for all molecular species we tested in our code and averages them out to show an overall confidence level of the simulation compared to the observed data around the protostar. With this plot, it becomes a lot more clear that the 100K and 200K models are the most accurate overall, especially in the time range we're looking for. The data for individual species may be more accurate for certain parameters. However, the most accurate simulated models we ran overall were the warm-up models for the 200K and 100K, both of which incorporating gas grain chemistry. In conclusion, this project shows that individual species simulations may vary in accuracy with observed data, and that's important to know. The exact formation processes and reaction data in protostellar environments for many molecular compounds is not known, but through simulation we can get closer to understanding them. The data also shows a strong accuracy compared to the protostar data with the average of the 100K and 200K models, which tells us we likely properly simulated the environment in which this data was taken. In the future, we may look to add more molecules to the code that are not yet implemented, such as methyl mercaptan or CH3SH, and continue to run simulations in order to improve their accuracy and better understand the formation of molecules. Thank you for viewing my presentation.